So 3D. Now what makes 3D trig problems, for want of a better word, difficult, I suppose, is visualising the problem. Certainly if they don't give you a diagram. Sometimes drawing those 3D pictures can be quite tricky. What I try to do then is redraw the diagram, but a series of 2D diagrams. It's much easier to do trig when you're just looking at a two-dimensional shape. So we'll do this via looking at some HSC questions. Here's a 2003 question. So David's in a life raft, Anna's in a cabin cruiser. Oh, I see, David's lost. Searching for him. But fortunately, yeah, you gotta love maths in real life, don't you? Fortunately, they both happen to have a mobile phone on them, and they happen to be in reception area as well. Yes, I know. What a stroke of luck. Now, David tells Anna, who amazingly has changed how she spells her name, that he can see Mount Hope. So Dave's in his little life raft with his mobile phone, rowing with one arm. I can see Mount Hope. Okay. Now, he also fortunately has equipment so he can work out, hang on a sec, Mount Hope's on a bearing of 109 degrees, and if I'm not mistaken, get out my clinometer. Ah yes, the angle of elevation is 16 degrees, because these are the sorts of things you keep in a life raft. Yeah. No room for the rations and the supplies, but we've got the clinometer and the compass. Now Anna, well, she's on the cabin cruiser going, well, that's a coincidence, I can see Mount Hope as well. Hang on, let me take some. She also has hey, from where I am, it's got a bearing of 139 degrees and the angle of elevation is 23. And they both happen to know that the height of Mount Hope is 1,500 metres above sea level. So thank goodness, whoa, now we can work out the distance and the bearing of the life raft from where Anna is. How lucky were they to have all that equipment there? As I say, maths in the real world. Okay, there's the diagram that they gave us. I don't know, it looks a bit bigger than a cabin cruiser. And there's poor little David in the life raft there. No. They might have had all those geometrical instruments. They can measure the height of Mount Hope. They can work out the angle of elevation. They can work out the bearing. They just can't see each other. So it must be, well, I don't know yet. We'll find out in the problem, but it must be a really big distance away. They can't see each other. All right. So I'm going to redraw the diagram so they're in two dimension, and from that hopefully come up with a problem. I've got a right angle triangle there, DHB, with the appropriate information. I've also got AHB, so they share HB. The other one, of course, is looking down on them because we want to try and work out the bearings and everything. So David's bearings, Mount Hope's bearing, because B was the bottom of Mount Hope, was 109 from David. Anna said she was 139, and of course we want to find that distance there from Anna to David. So there's another triangle we've got to work with. So we've got some angles. We need to work out some sides, but I can use my two triangles at the top there. I can work out a length for AB and a length for DB, so we should be able to do that without too much bother. So in fact, let's do that. So BD over 1500, tan 74. So we know BD is 1574, and I'm not going to do all the working out again, and neither should you in an exam because it's exactly the same steps. It's fair enough to just go, well, similarly, AB will work out to be 1500 tan 67. Notice I didn't use the 16 and the 23. You'll find a lot of people write down the cotan, and I think, well, what's the point of that? I mean, your calculator hasn't got a cotan button, so may as well write it in terms of what we can use. So that's why I used the complementary angle there to have a tan ratio rather than a cotan ratio. All right, I've added that to our diagram there. So we're trying to find B. I've got two sides. Well, let's see, how many angles? All I really need is one angle, and I can use a cosine rule. Or if I can find two angles, I can use a sine rule. Let's see what we got. I'm going to draw another compass in there at Mount Hope. Now, playing around with that diagram, that I can see that NDB plus DB and what I've labelled as N double dash is 180, because that would turn out to be co-interior angles. So therefore DBN double dash is 71 degrees, and similarly I could work out ABN double dash is 41 degrees. Now angle ABD would be DBN double dash minus ABN double dash. Common angle, basically it's the same angle, I'm just describing them in two different ways. So that's, I don't know how you've been taught to write that one. I just usually write common angles for that, because what I'm saying is, hey, same angle, just different way of describing them. So it's common. ABD turns out to be 30. Okay, there's the angle I was looking for, which allows me to now use the cosine rule. So it's just a cosine rule question now. So b squared equals 1500 squared tan squared 67, 1500 squared tan squared 74 minus 2 times 1500 tan 67 times 1500 tan 74 cosine 30. Punching all the buttons in the calculator, don't forget to go square roots, and you get 2798.96 dot 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 dot. So 2799 metres to the nearest metre, so it's almost 3 kilometres, so I suppose fair enough, maybe they can't see them when they're standing on the cabin cruiser. Okay, now that was the distance. I think the other thing I said was find the bearing, so the green bearing that I've labelled theta there. Well, we know to the blue line is 139. If I can work out angle BAD, add it on, we'll have our bearing. So I guess that's what I want to do. I want to find angle BAD. Now I can do that with a sine rule. I didn't bother writing 2799 for B, you'll notice I just left it labelled as B, because I'm going to use the exact angle that I've got on my calculator, not the approximation. Because you never know, certainly with trig, just a slight change in a decimal point can really have a huge difference sometimes. So subbing all that in, we want DAB. Now I get two possibilities, 69 degrees 9 or 110.51, because it could be obtuse. But if we look at our diagram, and the way I rationalise it out is, hang on a sec, if DAB is 69 degrees 9, and remember we found the other angle, so the third angle would end up being 80 degrees 51. But we know the biggest side must be opposite the biggest angle and so on. DAB actually has to be bigger than BDA. So therefore DAB can't be 69 degrees 9. It must be the obtuse angle. So I guess that was a little twist in that the question that year. You can imagine with all that working out, people would have gone, the calculator would have said 69 degrees 9, and people would have been more than happy to go, oh brilliant, that's my answer. But you see, hang on, you've got to think about it. Could it be obtuse? And in this case, it does turn out to be obtuse. So, if that is 110 degrees 51, our bearing, we've got to add that on to 139, we get 249 degrees 51 as our bearing. Okay, let's look at another one. So we've got another triangular prism here. A surveyor stands at point A, due south of the tower OT, angle of elevation 45, that's nice. Looks like we're going to have a whole heap of exact values, so it looks like they were quite nice that year in the year 2000. The surveyor then walks 100 metres due east and so on. Okay, so they've given us all the information. What you'll find in the HSC, and hopefully assessment tasks as well, is they usually describe the problem in both ways. They'll give you a diagram, so they'll give you a visual description of the problem, and then they'll write it in words as well. So they should back each other up. We want to find the length of OB in terms of H. Okay, looking at the diagram, I can get a triangle, OTB, it has H in there, and it has OB. So OB over H would be tan 60. Notice I went with the tan rather than the cotan again. So I've written it as H tan 60. Obviously, if you wrote it as H cot 30, it would still be okay. show that h is 50 root 2. Okay, well there's another triangle in there with h, ATO, but it's our classic 45-degree right-angle triangle, which we know is isosceles. So from that we can say, well, AO must be the same length as h. And now another right-angled triangle, we've just worked out the hypotenuse of that one is h tan 60. We know AB is 100. Bit of Pythagoras now. We can work out, eventually, 100 over root 2. We're going to get there. Whew, finally. So 50 root 2 for h. So we've shown that. Calculate the bearing of B from the base of the tower. Okay, so let's draw the ground. The base of the tower was O, so that's where I'm going to put my compass. And so that was due south. We now know that's 50 root 2. And nicely, it was due east. B was due east of A, so we've got a right angle triangle there. So we're not going to have to worry about a sine or a cosine, or we can use normal trig. Now, the bearing would be that green angle in there. But if I can find angle AOB, subtract it from 180, we've got our bearing. So I think that's what we'll try to do. So tan is 100 over 50 root 2. So 44, take that away from 180, we get 125/16 for our bearing. Alrighty. So 2G will do the odds and 2H will do the evens, just to mix it up a bit there. But you'll notice, or may not have noticed, I've set down Monday for this as well, because we've only got a single today, single on Monday. So we'll use both days to look at these 3D questions, I think. Okay.